Hi, my name is Duri Andrea Janett, and I'm going to talk about truly supercritical trade-offs for resolution, cutting planes, monotone circuits, and Weisfeiler Leman. This is joint work with Susanna, Noah, Jakob, and Schuh. So let me start by explaining what a trade-off result is. Take a computational model and two complexity measures for that model. For example, you could imagine mu to be time and nu to be space. Then, for a given computational task, we can consider how these two measures interact. First of all, we have some worst-case upper bounds on both of these measures, which I've drawn here as the dashed lines. A simple brute force algorithm will be able to achieve both of these worst-case upper bounds at once. We can see that there is a trade-off behavior if, to optimize one of the measures, we have to push the other measure towards its worst-case upper bound. For example, you can see here the upper blue dot optimizes nu at the expense of mu. A trade-off result will then be these two blue dots, that is, two upper bounds, together with an impossibility result, saying that you cannot optimize both of these measures at once. In 2016, Razborov introduced a new kind of trade-off result, where this red box indicating that it's impossible to achieve this combination of the complexity measures extends beyond the worst-case upper bound in one of the measures. For our example, this means that optimizing mu pushes nu way beyond the brute force worst-case upper bound on it. Such a trade-off result was later on called to be a supercritical trade-off. Now let us have a look at how Razborov proved this result. This is by a technique that is now known as hardness condensation, where we take a medium hard input in variables x1 through xn and then condense it. We do this by substituting each variable xi with an XOR over a subset of some fresh variables y1 through ym, where the condensation happens because the number of fresh variables m is much smaller than the number of original input variables n. If we can then show that the hardness is nearly preserved, the hardness will now be supercritical because it is measured in terms of m rather than n. This technique was further applied in a number of works and has led to many trade-offs in proof complexity, but also in finite model theory. One shortcoming of all of these results, however, is in terms of what you measure the supercriticality. Namely, they are supercritical in terms of the number of variables. However, this condensation technique considerably blows up the size of your instance, and hence if you measure the hardness in terms of the actual size of the instance, these results will not be supercritical anymore. This holds true for all previous trade-offs in the supercritical regime, except for these previous works that even predate Razborov's paper. This begs the question whether there are truly supercritical trade-offs, meaning trade-offs that are even supercritical in terms of the input size. In our work, we address this question. We get truly supercritical trade-offs for different combinations of parameters and proof systems, as well as monotone circuits and Weisfeiler Leman. This answers open questions in several works. Next, I will give you more precise statements of these results, as well as the necessary preliminaries to make sense of these statements. We start with the resolution proof system. Here, we operate on CNFs, and we want to prove that the CNF is unsatisfiable. Such a proof of unsatisfiability will be called a refutation. So, given the clauses of a CNF, we will be able to apply one rule to them, meaning that we can derive from C or X and D or not X the clause C or D. So as an example, let us consider the CNF consisting of the clauses drawn up here on the top right. Now we see that in the first two clauses X and not X appear, so we can apply the resolution rule to these two clauses. This then gives us the clause U or W or Y or Z. We now see that the next clause consists of the literal not Z, so we can apply the resolution rule to this clause and the one that we just derived to get rid of z, and similarly for y, w, and u. Now we have derived the empty clause, and since the resolution rule is sound, this means that because the empty clause is unsatisfiable, the original formula was also unsatisfiable. We will be interested in the following three complexity measures for resolution. First of all, the size of a proof, which is the number of nodes in the proof. Looking at the proof that I've drawn here on the right, this will be 11. Then the width of a proof, which is the maximum size among the clauses appearing in the proof. So in our proof, this is 4 because of the first clause that we derived. And finally, also the depth of a proof, which is the length of the longest path inside the proof. Since we are talking about supercritical trade-offs, we should also be aware of the worst case upper bound on all of these measures. So namely for the size, we have 2 to the number of variables. For the width and for the depth, we have linear in both cases. I should also say that if the DAG that is underlying our proof, such as in our example here on the right, is a tree, then this will be a tree-like proof. And we consider these complexity measures for a given formula by just taking the minimum over all possible refutations of that formula. So our results for resolution are as follows. First of all, we have a width-depth trade-off, meaning that we exhibit a family of CNF formulas Fn on n variables such that they can be refuted in somewhat small width, in that case polylogarithmic width, but getting close to this optimal width will require supercritical depth, even superlinear in the size of our formula. We get similar results for resolution size versus depth, meaning that we exhibit a family of formulas where optimizing the proof size requires supercritical depth, and width versus size, where this result only holds for tree-like resolution. So optimizing the width of these proofs will lead to supercritical size in these proofs. Importantly, all of these results are supercritical in terms of the input size. Next up is the cutting planes proof system, where now we are not reasoning over clauses, but rather over linear inequalities. We can translate a clause into a linear inequality as follows. So not x or y or z will be translated to 1 minus x plus y plus z is at least 1. We have the following derivation rules at our disposal. We have addition, where we can add linear inequalities, multiplication, multiplying linear inequalities by a scalar, and division, where we divide with a scalar. And note here that we are rounding up on the right-hand side. This is, of course, sound only over the integers. We can again consider the same example as before, where I have just translated our clauses into linear inequalities as in the example. And now we see that all the resolution steps we did before we can just replace by an addition. And note that we are not deriving the empty clause, but rather the trivially false inequality 0 is at least 1. The complexity measures of interest this time around are size and depth, where size is again the number of nodes in our proof DAG, and the depth is the length of the longest path in our proof. We again have the following worst case upper bounds, so size needn't exceed 2 to the number of variables, and worst case depth can always be made to be at most linear. So with the proof systems that we are going to discuss at hand, I should also introduce some formulas. These are going to be the Zetin formulas, which is one of the main workhorses of proof complexity. They encode the handshake lemma from graph theory. So given a graph and the labeling of its vertices to 0 and 1, such that all the labels sum to an odd number, we will introduce a variable xe for every edge e in the graph, and then we will consider all the constraints saying that for every vertex, the sum over all the edges incident to that vertex will be equal to the label of the vertex mod2. Taken together, these constraints are clearly contradictory because it says that the sum of all degrees in a graph is odd. However, the handshake lemma requires that this sum must be even. So an example of how this will look like as a CNF is the following graph. So consider the top left vertex. Here the constraint says that XA XOR XB must be equal to 1. Expanded into CNF, we get the two clauses drawn in orange. Similarly, we get the clauses in orange for the vertex on the top right, on the bottom left, and on the bottom right. Note also that we have only one vertex with label 1, so the sum of all labels is equal to 1. Ever since this was introduced by Zetin, these formulas have been extensively studied. They have in particular led to exponential resolution size lower bounds and have also been studied for numerous other proof systems such as sum of squares, bounded depth Frege, stabbing planes, etc. Now, a long-standing conjecture in proof complexity was that Zetin formulas should also be hard for the cutting planes proof system. However, this was somewhat recently refuted by Dadouche and Tivari, which exhibited quasi-polynomial size cutting planes proofs for the Zetin tautologies. It is also known that cutting planes requires linear depth to refute the Zetin formulas, and it is notable that the refutations exhibited by Dadouche and Tivari have supercritical depth that is also quasi-polynomial. This leads to the interesting question whether Zetin formulas actually exhibit a supercritical trade-off for size versus depth in the cutting planes proof system. One indication that this might be true is given by the previous work of Fleming, Pitassi, and Robert, which exhibits a supercritical trade-off for a different kind of formula in the cutting planes proof system. This trade-off is again supercritical in terms of the number of variables. This brings us to our result for the cutting planes proof system, which is a size-depth trade-off. Namely, we exhibit a family of formulas which can be refuted by cutting planes in quasi-polynomial size, but approximating this optimal size requires supercritical depth, which is superpolynomial even in the formula size. Again, this is a supercritical trade-off in the input size and not just the number of variables. I should, however, note that this does not resolve the question for Zetin formula, which remains open. However, Zetin formulas were used in the construction of our formula family, which has the provable trade-offs. Finally, let us get to monotone circuits, which are circuits consisting of only AND and OR gates, so in particular there are no NOT gates. They compute Boolean functions going from 0, 1 to the n to 0, 1, and you can see an example here on the right-hand side. We're going to be interested in the complexity measures of size and depth, where size is again the number of nodes in our circuit and depth the length of the longest path. For worst case upper bounds, we have that the size can always be made to be exponential and the depth never needs to be more than linear. Previous work on size-depth trade-offs for monotone circuits led to this non-supercritical result where linear size circuit exists but has to have close to linear depth. Our result for monotone circuit is the following supercritical size-depth trade-off. Namely, we exhibit monotone functions fn on n variables such that they can be computed by a monotone circuit of quasi-polynomial size, but optimizing the size will require depth even superpolynomial in the number of variables. I will now tell you a little bit about our proof, which is structured into a base result to which we are then going to apply lifting theorems to get our other trade-offs. So first, I will discuss the base result. Here you can see our base result, which is in fact our resolution width versus depth trade-off. We show that for parameters c and k, depending on n, there are 4 CNF formulas such that the size of these formulas is roughly n to the c. They can be refuted in width k plus 3, but any width below k plus c proof will require depth at least the size of the formula to the k over c, so superlinear in the size of the formula. This result is proven via a technique that we would describe as variable compression that goes back to a recent paper of Grohe, Lichter, Neuen and Schweitzer. So if you want to go back to our picture from one of the first slides and compare it with the hardness condensation by Rasporov, where we substituted original variables with XOR gadgets over the fresh variables. In this variable compression technique, we instead directly substitute the fresh variables into the original variables. Of course, to achieve a compression, this will then have a lot of collisions. So for our instance, we're going to consider the Zetin formulas as I've introduced them before on a long and skinny cylinder. Namely, this means that the edges wrap around vertically but not horizontally. For the labelings of the vertices, we will have a single vertex labeled 1 at the top left and all the others will be labeled with 0. We are then going to split our cylinder into 3 parts, leaving a small number of columns on both the left and the right end. And on this large middle part that we now have, we're going to start identifying vertices. Namely, we're going to put for every row a vertex equivalence class on that row. In particular, for every row we are going to pick a modulus mi, and then we're going to say that the vertices at the distance of this modulus mi on a given row are equivalent. Again, we're going to do this only on the middle part, so we're going to leave the ends that we split off before without any identifications. This will then induce an equivalence class on the edges, and we will use this to define a compressed Zetin formula as follows. So now we're going to have a constraint for every vertex equivalence class saying that summing over the variables for all the incident edge equivalent classes, we should be equal to the label of the vertex equivalence class. Let me note that we now have a variable not for every edge, but for every edge equivalence class. Similarly, we only have a constraint for every vertex equivalence class, which allows us to shrink the formula size. Zooming in between 2 rows, the edge equivalence class will look as follows. So in particular, here we have picked M1 to be 6 and M2 to be 15. And below, I should again point out that for every color you see here, now there will be only one variable in our formula. So how will we go about analyzing such an instance? Well, first, let me tell you how we would analyze this instance without any compression. So how do we analyze resolution refutations of the Zetin formulas? This goes via a cop-rubber game, which was introduced by Seymour and Thomas in the context of tree width, actually. And the rules are as follows. So we start with k cops on the graph and 1 rubber at an initial vertex, which will be v0. And in each round, play will go as follows. So 1 cop will enter the helicopter and signal a vertex v where he's going to land. Then the robber can move, but he has to move in such a way that he doesn't run into any of the cops. Finally, a cop will land at the vertex that was initially signaled. The game ends when the robber is caught. This means that a cop lands at the same vertex as the robber is currently standing. Now, what was previously known is that the width of a resolution refutation of the Zetin formula defined on a graph roughly corresponds to the number of cops in play, and the depth of that same refutation to the number of rounds it takes those cops to catch the robber. Note, however, that this correspondence is only approximate, so it's not quite precise. So for upper bounds on our refutations, we can now just exhibit cop strategies. For example, in the case where we have k plus 1 cops, the cops have a very simple strategy. Namely, they just form a police cordon on the middle, cutting the graph into 2 parts, and then march to the robber. This will take them k times L many rounds, roughly. This then translates into a resolution proof of width k plus 3 and depth k times L. So note that here the width isn't exactly the number of cops, as I've hinted at on the previous slide. If you have much more cops, namely 3k cops, we can do something that will catch the robbers much faster. Namely, we can do binary search, where the cops can now form these cordons and always have 2 at a time on the graph, and like that do binary search for the robber. This translates into a resolution proof of width 3k and depth k times log L. So note that by paying a little bit in the width, we have achieved an exponential decrease in the depth. But now, since we are not analyzing the vanilla Zetin formulas, but rather the compressed ones, we will also need a compressed game. This goes back to the paper of Groh et al. As the construction does. In this game, we now have a cop at the vertex equivalence class rather than just at a simple vertex. The rules are that we have k plus c many cops and 1 robber starting at v0. In every round, we lift a cop to the helicopter, and this cop signals again a vertex. The robber then has to do a special type of move, which we will call an equivalence compressible move, before the robber lands at a vertex equivalence class. The cop strategies from the uncompressed game will of course still work, so we will get the same upper bounds for the compressed formula as we had for the original formula. However, the robber now has to avoid not just the cops but also the cop clones and do these special types of compressible moves, so it will be much harder to get lower bounds. To exhibit the lower bounds, we will consider only a special type of robber moves. So let me describe this special type of a robber move. The robber will constrain himself to move only on a set of I contiguous rows, which will be of size at most c plus 1. This will ensure that there is some row where there is a unique cop. Furthermore, the robber will repeat his move periodically, namely with periods GCD of the row moduli of all the rows that he's touching. This will ensure that if he avoids the cops in one of the periods, he avoids them in all of the periods. So with the robber moves at hand, I can now give you a general idea for the global strategy that the robber is going to use. He's going to stay on a cop-free column in the left or the right part of the cylinder. As you may recall, in these parts of the cylinder, there is no identification among the vertices. He will then slide between these 2 sides of the graph whenever necessary, using the compressible moves that we described before. The main problem that the robber will encounter is that the cops can form police cordons, which is the case when they cut the graph into 2 parts. What is particularly difficult for the robber is that the cordons can also be formed between clones, so they might appear in many places at once. So the robber has to use the following strategy to avoid being trapped by the cordons. he will keep away not just from the actual cordons that the police is currently forming or could occupy in the next move, but from a much more general set of virtual cordons, which encompasses all the possible police cordons that could be formed within the next move. This will allow the robber to escape to the other side of the graph in time. However, the police cordons will only be able to move very slowly. This is due to the fact that there will be a row with a unique cop in there. So to not break the cordons, the police will have to move slowly. This allows the robber to survive roughly n to the k rounds against k plus c cops. Going back to how we constructed our compressed cylinder will allow us to see what kind of parameter this gives us. So again, we fix parameters c and k, and then we pick k coprime numbers roughly of size n, and we pick the ith modulus to be 4k times and then c plus 1 many of the primes, where for every row we pick a different set of consecutive primes. The length of the cylinder will then be roughly 4k times p1 through pk, but the length of the compressed formula, or the size of the compressed formula, will only be of the same magnitude as the moduli. So the formula size will go down from n to the k to n to the c plus 1. And if you recall, the robber can survive for n to the k many rounds. I now want to go back to the work of Grohe et al., which is what our construction is based off of. This work considers the Weisfeiler-Leman algorithm, which is an iterative procedure that refines colorings of tuples of vertices of a graph. This can be used as a partial graph isomorphism test and has also been connected to many other areas. And namely, Grohe et al. Showed the following trade-off between the dimension and the iteration number of these algorithms. So I should say that the dimension of the algorithm is the size of the tuples whose coloring is being refined, and the number of iterations is the number of refinement steps until this coloring stabilizes. So Grohe et al. Exhibited graph pairs which can be distinguished by the k-dimensional Weisfeiler-Leman algorithm, but only after n to the k half iterations. This Weisfeiler-Leman procedure is related to resolution of Zetin formulas in the following sense that dimension roughly corresponds to the width of the refutations, the number of iterations roughly corresponds to the depth, and the graph pair to the Zetin instance. However, since this result only holds for one particular dimension k, and the correspondence between dimension and width isn't exactly tight, this result is not robust enough to yield proof complexity consequences. However, since our construction essentially generalizes theirs, we can get the following slightly more robust trade-off for the Weisfeiler-Leman algorithms. So for C between 1 and k minus 1, there are graph pairs of size n, which are distinguished by the k-dimensional Weisfeiler-Leman algorithm, but a lower bound of n to the k over c plus 1 holds up to the k plus c minus 1 dimensional Weisfeiler-Leman algorithm. So getting back to the proof plan from the introduction, we now have covered our base result and are ready to try and apply some lifting theorems to get our other trade-off results. So what exactly is a lifting theorem? So lifting is the idea to use composition to relate different models of computation. In particular, we want to relate the complexity of some instance f in model A to the complexity of a composed problem f composed B in model B. And typically F will be the complexity of F will be measured in a weak model, and then the composed problem will be measured in a stronger model. As an example, and what would be quite handy for our result here, we could have something like, if the formula F requires large resolution width, then once we compose it with some gadget G, F composed G requires large resolution, cutting planes, or monotone circuit size. So how do we compose instances? I'm going to show this only for functions, but this can also be extended to CNFs. In particular, we want to take a function f from 0, 1 to the n to 0, 1 and compose it with the index function. As you can see here, the index function has a split input, so it takes input in the numbers from 1 to m times 0, 1 to the m and outputs a single bit. So we can imagine that this input is split between two parties, Alice and Bob, where Alice gets a number from 1 to m and Bob gets a bit string of length m, and then Alice just points into Bob's bit string. In particular here, Alice would point to the first location of Bob's string, so that's a 0, so the output of this index function would be 0. But now we want to compose a function with n input bits with this indexing function. So we need to do this n times. So in particular, Alice gets n many numbers of between 1 and m, and Bob gets n bit strings of length m. And then Alice just points into Bob's matrix, and this will be our new input to our function f. So for example, in the second position here, Alex has a 3, and this points to a 1 from Bob's side. So the second bit of the input to our function f will now be a 1. So now we want to go from resolution to monotone circuits, and here there is this previous work of Garg, Gös, Kamat, and Sokolov, which in our case tells us that we can go from a resolution with depth trade-off to a monotone circuit size depth trade-off. So what does the result say? Given a CNF formula f, we can construct a function little f such that a size m to the w depth d monotone circuit for little f implies a width order w depth order dw resolution proof for big F. So in particular, if you have a trade-off in the model below here, the second model, this will imply a trade-off in the monotone circuit model. One crucial issue here is that the number of variables in the function that we construct roughly correspond to the number of clauses in the formula that we use to lift with. So this means that previous supercritical trade-offs couldn't be lifted because the formula size there was too large. So it is crucial that the depth-width trade-off is in fact truly supercritical. A second issue in our case is that the width of the extracted resolution proof is not quite of order W. And since we only have this somewhat small robustness in our trade-off, namely from k to k plus c, we needed to prove a tighter lifting theorem with better constants to be able to apply it to our width depth trade-off. This is in fact what we managed to do. So here is the essentially tight lifting theorem for monotone circuit that we also prove in this work. And it says that, again, constructing the same function little f from a formula big F, we have that a size m to the 1 minus epsilon w depth d monotone circuit for little f implies a width w depth WD resolution refutation of big F. This is almost optimal except for the 1 minus epsilon factor in the exponent, and also applies to the cutting planes proof system. So this gives us both our results for monotone circuits and cutting planes. So as a corollary from our theorem above, we get our size-depth trade-off for monotone circuits. Finally, I should also discuss some concurrent work that is actually appearing in the same conference, which is by Göss, Maistre, Risse, and Sokolov from EPFL. They independently also obtained supercritical size-depth trade-offs, in particular for monotone circuits. The general structure of their proof, namely lifting base with depth trade-off, is the same. However, their width depth trade-off is based on a completely different formula, which formalizes a new and interesting combinatorial principle. This trade-off is inherently very robust, and this robustness in fact allows them to use existing lifting theorems from the literature as a black box. In contrast to our work, they have a different parameter regime. So in particular, their parameters are very robust, but ours kick in a little bit earlier. So we get a result also for constant width, and our depth lower bound is near optimal. We also get applications to the Weisfeiler Leman algorithm and continue the line of work on this compression technique that was introduced in the paper of Grohe et al. And by necessity, we also prove tighter lifting theorems, which might be of independent interest. So finally, let me get to some open problems. The first thing we would like to ask for is further applications of this compression idea in proof complexity. One candidate that might be interesting are pebbling formulas, because they are also based on graphs. Another thing that could be worth trying is to find other graphs and graph compressions to apply to Zetin formulas. We would also like to see more supercritical trade-offs in general, for example, with respect to space or similar, and it could be interesting to get a unified parameter range with the concurrent work of Göss et al. For the width, depth, in resolution. Perhaps more ambitiously, we would like to ask if the complexity of Zetin formulas for cutting planes exhibits a supercritical trade-off, and also regarding monotone circuits for the bipartite perfect matching function. Here, superpolynomial lower bounds are known for quite some time, and it is also known that linear depth is necessary. So could it perhaps be that there is a supercritical trade-off there? To conclude, we have shown truly supercritical, meaning that they are supercritical even in terms of the input size, trade-offs for several proof systems and combinations of parameters, as well as monotone circuits and the Weisfeiler-Leman algorithm. This is proven by lifting a base trade-off, which is going to be the depth versus width trade-off. This trade-off is shown for a compressed Zetin instance, which is analyzed via a Kopp-Robber game. We also need to improve the existing lifting theorems in the literature to achieve our other results. For future work, we leave the following questions. Is it possible to compress other formulas in proof complexity or graphs other than cylinders? Can we prove supercritical trade-offs for other measures such as size versus space? And are there supercritical size depth trade-offs for Zetin formulas in cutting planes or for bipartite perfect matchings in monotone circuits? With that, I thank you for your attention.